conversion and the rigidity. Let's welcome. Yeah, please.
Yeah, thanks, Chang Liang, for the introduction, and I'm very happy to attend the convergence or scalar curvature workshop. So today I'm going to talk about the recent work joined with my collaborator, Dongyang Ku, about the scalar curvature comparison and rigidity. So let's begin by recalling the Gauss-Bonnet formula for the compact surfaces. So we all know that, so given the two-dimensional compact surface omega, the integral of the Gauss curvature on omega and the boundaries geodesic curvature is equal to 2 pi times the Euler characteristic of omega. So actually this is a smooth version. So also you have like a, if your boundary is a piecewise smooth, you can also have a Gauss-Bonnet formula, for example. Let's see. So if your boundary is piecewise smooth, so the Gauss-Bonnet formula is written as the integral of the Gauss curvature, boundaries like the smooth parts geodesic curvature, and also summation of pi minus alpha I equals 2 pi Euler characteristic of omega. So here is like the angles alpha I. Okay, so actually we have like an intuitive understanding of the piecewise smooth version of the Gauss-Bonnet formula. So, so basically, if you are considering some like in Euclidean space, and so you have some alpha here, so you use some very small arc to approximate the singularity. So, so for example, you use the arc with radius r to approximate this singular curve. So in this case, you can actually see the geodesic curvature of this arc is exactly 1 over r. And if you integrate on the arc of the geodesic curvature, you actually get pi minus r. So this is the geodesic curvature of the approximate curve. And if you do some integral on this curve, it gives you pi minus alpha. So this is an intuitive understanding of the piecewise smooth version of the Gauss-Bonnet formula. Okay, so in Gromov's 4 lectures on scalar curvature, he formulated the following polyhedron comparison conjecture. So Gromov's conjecture. It says that, okay, suppose you have a convex polyhedron in Euclidean space, like P. This is a convex polyhedron. And if you equip P with a Riemannian metric G such that the scalar curvature is non-negative, and on the face, the mean curvature is non-negative, and also on the angle, you have some like angle comparison. The angle of the G metric is always less or equal than the angle with respect to the Euclidean metric. Then he conjectures that G must be Euclidean. Okay. So of course, in dimension 2, it follows directly from the Gauss-Bonnet formula. It follows directly from Gauss-Bonnet formula. Okay. So in higher dimensions, so Li used the capillary minimal surfaces in dimension 3. So he used the capillary minimal surface in dimension 3. And he proved that two special types of polyhedron, the Gromov conjecture is true for two special types of polyhedron. So two types. So the first type is what he called a cone type. And second type is what he called a prism type. Basically, it has like two bottom which are parallel. Okay. So this method is using capillary minimal surface, which is closely related to our work. Wang Xieyu they developed the spin geometry on manifold with corners. To prove the Gromov's conjecture. And later, Brendel used the smooth out procedure and spin geometry to prove Gromov's conjecture under the matching angle hypothesis. Okay. And also Brendel Wang also used spin geometry and another smooth out procedure to prove Gromov's conjecture for the acute angle comparison. So basically the angles are all less or equal than pi over 2. Okay. So here is the history, some history of the proof of the Gromov's conjecture. So it is actually a natural question to ask, like because you see in for the Gauss-Bonnet formula you can have a polyhedron comparison thing in dimension 2. You also have a smooth version. So a natural question will be, do we have a smooth version of Gromov's conjecture? So do we have smooth version of Gromov's conjecture? So actually, Gromov proved the following extremity result for standard unit ball. Okay, so Gromov proved. So this is by Gromov. So it says that okay, this is a three-dimensional compact domain whose boundary is actually diffeomorphic to a two sphere. Okay, that's 2. And under this diffeomorphism, you can do some comparison, which is the mean curvature comparison. So the first comparison. So H0 is the standard sphere's mean curvature, and also the metric comparison. on the boundary, restricted to the boundary. So everything with a bar. So here in our notation, everything with a bar is a quantity in Euclidean metric. Okay. And recently, Chai Wang generalized Gromov's extremity result to any S1 rotational symmetric domain in Euclidean in three-dimensional Euclidean space. So they generalized the S1 rotational symmetric convex domain. In R3. So they also used some changing angle capillary minimal surface technique. Okay. So now in this talk, I will, so our result is actually the follows. Okay. So suppose that M3 is diffeomorphic to some weakly convex and mean convex domain in R3. Domain in R3. Okay. So assume further that if you equip M3 with the metric G such that the scalar curvature is non-negative, and on the boundary it satisfies what we called the scaled mean curvature comparison. H square G restricted to the boundary is greater or equal than H naught square G Euclidean restricted to the boundary. And assuming that M satisfy one of the following cases, so assuming M3 is one of the following. So it can be any smooth domain. Okay, so M3 is smooth, or it is a prism type, or it is a cone type. Angle comparison at the vertex of the cone. Then G must be Euclidean. Okay, so let me add a few remarks here. So the first thing is that we do not, so M can be any smooth domain in R3. We do not assume any symmetry on M. The second thing is that when we use the terminology prism type and the cone type, it's not exactly the same as Chao Li's definition of the prism type or cone type, because when he defined the cone type and prism type, he actually defined it only for polyhedron. So here we actually generalize this definition a little bit to some like domains in R3. So basically, so let me draw a picture here. So it has a, if it's a domain, which has a cone point, but other parts are smooth. This is what we call a cone type. Okay, so prism type is similar. It's something like two is like sigma 1 and sigma 2, they are actually parallel barriers. And other parts are smooth. This is what our prism time. Basically, they're just generalization of Charlie's definition for prism time and cone time. Okay. So let me see more words about our capillary minimal surface method. Okay. So let's start with Charlie's capillary minimal surface method. So let me draw a cone type polyhedron in dimension 3. So actually, he assigned like on each, so there is an angle. So for each surface here, this is an angle theta I. So he actually assigned the capillary function theta I for each faces sigma I. And the bottom is actually serving as a barrier. And you find some capillary minimal surface with prescribed angle theta I. For different faces, contact angle is different, it changes, but it's always equal to the contact angle of the surface and the bottom. So this is they use the constant capillary angle. So our model case is like it's only focused on the smooth case. So our model case is basically any weakly convex domain, weakly convex and mean convex domain in Euclidean space. So this is our model, and it has no symmetry. So we just pick an axis, z axis. So and it intersects with a point P. Actually, we need, so this P is not that arbitrary. We need to make sure that at P, the mean curvature is strictly positive and the determinant of the second fundamental form is strictly positive, but I mean, it's fine because you can always choose a P like this. This is not difficult. And we have some Z axis. So now we no longer have the barrier. Actually, we use the xy plane, which is perpendicular to the z-axis, to slice this whole domain. So we slice this whole domain like this. So for each point on the boundary of N, so for each point x, there is an angle, which is the capillary angle. We call it rho bar x. So now we defined the rho bar function for any point on the boundary of M. And this is actually our capillary functional. Okay, more precisely, we define the capillary functional as like this. Okay, so what is our omega? So omega is basically any domain here containing the point we choose, the point P here. Okay, so here partial I omega is defined as real of M, basically this part, okay. And the partial B of omega is defined as boundary of omega intersect with boundary of M, okay. So now suppose we can have a non-trivial minimizer like in our geometric, for the capillary functional, then so okay, let's take a look at its first variation, second variation. So here we use sigma to denote the partial I omega. So basically that's so now we do the first variation. Okay, before we start, let me let you know our let you know our like notations. Okay, so this is our sigma. So this is our sigma, and the unit normal of sigma in M is denoted as M, and the unit outer normal of the boundary of M is defined as X. Okay, so the unit tangent vector of boundary of sigma is denoted as tau, and the outer unit normal of the boundary of sigma in sigma is defined as eta, and the unit outer normal of boundary of sigma in boundary of M is defined as nu. Okay, so everything here we write. If there's no bar, then everything is in geometric. If we add x bar or eta bar, nu bar, tau bar here, or n bar here, that's the corresponding vectors in the Euclidean case. Okay, so the first variation actually gives us, so 0 is minus mean curvature of sigma times f plus on the boundary y eta minus nu cosine rho bar g. We actually consider the variation per psi, which is from minus epsilon to epsilon times sigma to m. And actually f is defined as y n g, where y is d per c dt at t equals 0. And it's obvious that y is actually tangential to boundary of M along boundary of sigma. So y is tangential to boundary of M along boundary of sigma. Okay, so this is our first variation. So if sigma is actually a minimizer, what we know is that this sigma is a minimal surface, and it intersects with the boundary of M with the capillary prescribed capillary functional rho bar x. Okay. So the second variation is actually minus sigma f plus a square Ricci and f square plus boundary of sigma f df d eta minus qf, where your q is 1 over sine rho bar nu minus cotangent rho bar a eta plus sine rho bar cosine rho bar. So now this is just by direct computation. Okay, so now you just take your you can just take your f equals 1. Okay, so you just take your f equals 1. And the second variation is non-negative if it is a non-trivial minimizer. Of course, it is stable. So if you take your f equals to 1, what you get is minus of plus Ricci and on sigma is greater or equal than on the boundary the integral of Q. So here we use a lemma of Chai Wang, where they wrote that they observed that they actually observed that you can rewrite your Q. So you can rewrite your Q as minus H cotangent rho bar plus H boundary of M over sine rho bar minus the geodesic curvature plus 1 over sine rho bar square d nu cosine rho bar. Okay. So why this is true? Okay, this is so let's go back to this picture. You will see the definition. So you will see that because sigma actually intersect the boundary of M with prescribed angle rho bar. So you actually have x n g equals cosine rho bar. So actually you can write your x as cosine rho bar n plus sine rho bar eta, because x is of course orthogonal to the tau direction, and actually n tau eta, they form an orthonormal basis of the M3. Okay, so now you can see what is your second fundamental form of boundary M tau tau. Okay, so this is actually minus tau tau x. So you write x in terms of n and eta. Okay. So this actually gives you cosine rho bar a tau tau plus sine rho bar k. And you know that the mean curvature of sigma equals a tau tau plus a eta eta, and you just put everything in, and also you rewrite you write the boundaries second fundamental form tau tau in terms of the boundary mean curvature and the boundary and the second fundamental form of boundary input with nu. And rearranging the terms, it's pretty obvious that Q equals the right-hand side. Okay. So also you can further write it as H u of minus geodesic curvature plus 1 over sine square rho bar d nu cosine rho bar. This is because from the, so this is actually 0 from the first variation. Okay. So now we just, by taking this and rearranging the terms, and also Gauss trace the Gauss equation. So you can actually write this is less or equal to the integral of the Gauss curvature. So basically by arranging terms and use Chai-Wang's lemma, you can actually prove that by the second variation, you actually have boundary of sigma Gauss curvature plus the boundary's geodesic curvature is greater or equal to boundary of sigma sine rho bar plus 1 over sine square rho bar d nu cosine rho bar. Okay. So our key estimates is actually But on the boundary of sigma, the mean curvature of the boundary over sine rho bar square, so square should be here, the new cosine rho bar is greater or equal to 2 pi. Okay, because the sigma is definitely a disk. Okay, so the left hand side is basically 2 pi. If the right hand side is greater or equal than 2 pi, you can prove that everything you threw out must be 0, which includes the second fundamental form of sigma and also other terms. You can actually prove that the sigma is infinitesimally rigid. And then you can construct, by some standard argument, you can construct a local constant mean curvature surface near sigma, and you actually prove that they are all flat. And this gives you a local splitting. And then by the connectedness of the domain of M, you get a global splitting, which tells you that this is actually Euclidean. Okay, so let me try to provide more details on how can we get our key estimate. Okay, so this 2 pi here is actually a winding number. Okay, so the key idea of getting this estimate is doing projection. Key idea is projection. So for any point on the boundary, we have the following lemma, which in our preprint is 3.1. Okay, so the mean curvature, of course, with the G metric of the boundary, is always greater or equal than the Euclidean mean curvature over a square plus b square. Sorry, the square a tau plus b nu, a tau bar plus b nu bar with a Euclidean metric, where a square plus b square is non-zero. Okay. So let me explain a little bit. So what is your tau bar and nu bar? Okay. So let me draw. This is our domain, right? So this is your axis. Okay. So your Euclidean non-trivial minimizer are all horizontal slices. Okay. The blue horizontal slices. However, if you get in the non-trivial minimizer in the G metric, it's possible that your slice is not horizontal. It's like the blue curve. Sorry, the red curve. This is your sigma, right? So for any point on the sigma, so you have your tau, you have your nu. But this point also belongs to a horizontal slice in the standard case. Okay, so this point here also lies in a standard piece, sigma bar P. So it has some tau bar and nu bar. So basically we do projection. So for a vector, we just project everything to the standard direction. This is the idea. And it's actually fine because in the rigidity case, you are looking for some Euclidean domain. So everything here should achieve equality. Okay. So the proof is not so hard. It's basically from the scaled mean curvature comparison. Okay. This is from this. Okay. Just plugging in. So h squared g a tau plus b nu, a tau plus b nu. So this is basically h squared a plus times a squared plus b squared. And now this is greater or equal than, sorry, let me adjust this a little. So h squared g A tau plus B nu, A tau plus B nu. This equals h squared times A squared plus B squared. And this is by the scaled mean curvature comparison. This is greater or equal than h naught squared G Euclidean. A tau plus B nu, A tau plus B nu. And now we just choose the orthonormal basis for the boundary of M in Euclidean space as A tau bar plus B nu bar over square root of A squared plus B squared and another W. Okay, this is fine. So this is a norm of the A tau plus B greater or equal than the projection to the A tau bar plus B nu bar direction. So this is greater or equal than H G naught G Euclidean A tau plus B nu A tau bar plus B nu bar over square root of A squared plus B squared square. And just and the proof is done. Okay. Okay, this is our first lemma for the key estimate. Okay. Okay, our second lemma for the local estimate is where the weakly convexity plays its role. Okay. Minus the new rho bar is greater or equal than tau times rho bar nu bar plus h naught minus nu bar rho bar tau bar. Okay, G Euclidean. Okay, so to prove this lemma, we need two ingredients. Okay, the first gradient is h naught minus this. So what does this mean? Okay, let's see. In the Euclidean case, your n bar is actually EZ direction, right? If you recall the picture, we are using horizontal slices, which is perpendicular to the z-axis to slice the domain. Okay, so your cosine rho bar is actually x EZ G Euclidean. So d nu bar cosine rho bar is actually d nu bar x bar EZ. Okay. And then you can actually, so let's see. This is your EZ. This is your x bar. This is your nu bar. Okay. So actually you can write your you can actually write your nu bar as in terms of x bar and EZ. So your nu bar is actually minus sine rho bar EZ is and also let's see, this is rho bar, so this is rho bar. Okay, this is minus, this is cosine, this is your nu bar is, oh, I'm sorry, nu bar is perpendicular to x, I'm sorry for that. I was wrong. So you actually can write your new bar in terms of your EZ and eta direction and then you will see that this is actually equal to minus sine bar, the second fundamental form of new bar and new bar. Okay, sorry for that. And similarly, you can try to write tau bar cosine rho bar, which is equals to minus sine bar, second fundamental form of tau bar and nu bar. So actually, this thing, if you write everything together, this is basically the determinant of the second fundamental form of the boundary of M in Euclidean metric. Okay. The second ingredient is lemma 3.1. And then by some smart choices of the A and B and do some smart projections, you can actually obtain these estimates. Okay. So the next lemma, 3.3, is saying that if you have a gamma which surrounding a curve on the boundary, who actually separates the boundary of M into two parts, and is parametrized counterclockwise, and one part contains the point P, then arc tangent YU XU ds is some 2k pi. So k is greater or equal than 1 if it's counterclockwise parametrization. Okay. So now finally with this lemmas, we are able to prove our key estimate. Okay. So if you apply lemma 3.2 and write everything in parametrization of your gamma. So 3.2. And you write everything in parametrization of gamma. So you parametrize your gamma as gamma A. Then you actually, by direct computation, you are able to prove that. Okay. So then after you obtain the key estimate, you know that once you have a non-trivial minimizer, so once you have a non-trivial minimizer, then you can prove that they are all infinitesimally rigid. And then you can have some local splitting. So this local splitting actually is pretty standard. Chao also used this in his proof of the Gromov's conjecture for polyhedron, for some special types of polyhedron. So basically you need to construct some CMC and prove all the CMC you constructed are actually all infinitesimally rigid. And then you get the local splitting. And then by the connectedness of M, you get some global splitting. And then the proof is done. So how to guarantee that there is a non-trivial minimizer? So actually, you also need to use some to cook up some CMC foliation to use it as a barrier to guarantee the existence of the non-trivial minimizer. So like this. So you need to cook up some CMC foliation as your barrier. And then use this barrier actually guarantees the existence of the non-trivial minimizer. So however, the barrier is not that easy. So for example, in your smooth domain, so with your chosen P, so the idea is that you actually construct some CMC barrier near the point P with prescribed angle rho bar. However, since we do not assume any symmetry of the boundary, the parametrization of boundary of M is actually an elliptic parabolid. So you actually need to analyze the parametrization very carefully and use the implicit function theorem to construct some CMC with prescribed angle and non-negative mean curvature, which actually guarantees that 0 is not the minimizer of the so okay, so let me say it in this way, to guarantee that you can find a non-trivial minimizer of the capillary functional and run the argument above. Okay, so yeah, I think that's my talk today. Thank you.
So yeah, thanks, Xuan, for the talk. Any questions? Yeah, if questions, let's thank Xuan again. Thank you very much.
Thank you, Chuan Yao.